right, we are going. Can I get a mic check?
Hey, how's it going?
All right, good. Looking good, Hilding. Dr. Neilson, what do we call you?
Building's fine.
All right. All right, a little more.
Sorry?
Just a little bit more. All right, here we go.
All
Hello,
right.
I'm MC Toon, and this is the Toon Show, and I have with me tonight Dr. Hilding Neilson from the University of Toronto. Welcome, Dr. Neilson, or Hilding, as we should say.
Oh, thanks for inviting me. It's a pleasure to be here.
It's exciting for me to hear some of the details that you do, and to maybe have just a peek into what the kinds of things that you do, and the specifically about Polaris, because I deal a lot with flat earthers and they get everything wrong about every star, but mostly they get things wrong about Polaris. Now, we won't be talking about flat earthers necessarily, but I think it's just exciting, entertaining, and educational to figure out what it is that how do we figure out things about stars. So do you want to cover anything about your background so people know who it is that you are?
Oh, thank you. Yeah. So my name is Hilding. I'm an assistant professor at the University of Toronto in the Department of Astronomy and Astrophysics. And at least for a couple more months, I'm moving to a new institution in the summer. And yeah, so that's kind of basically everything about me professionally. I like work. I do a lot of work studying different kinds of stars and exoplanets, and never actually thought about how flat earthers deal with stars. So I'm kind of curious to learn something about that tonight.
Well, I'm sure we'll cover a bit of their silliness. So, all right. Well, now you've written some articles, and I have the link to your website and your About Me page in the description. And you've talked a bit about inclusion of Indigenous people in STEM, and more specifically in astronomy. Anything? I don't know much about that. Is there anything that we should maybe know, or that you'd want to?
Uh, um, so yes, I'm also a Mi'kmaq. That's an Indigenous group from northeastern Canada and northeastern United States. And in astronomy and physics, there are very few Indigenous, Native American, Inuit, Hawaiian people anywhere. The National Science Foundation barely counts it as a statistic because there's so few people.
Wow.
And so I've started working more towards inclusion because STEM needs more Indigenous peoples as well as many peoples of different races, different colors, different genders. It's such a white male dominated field that we need to change and grow. And it's come to a head in the last few years because one of the things astronomers like is telescopes. And we like the bigger the telescope, the better it is, so that we can see dimmer objects, see further into the universe. And we build them mostly on Hawaii. And a few years ago, when astronomy was about to break ground on a 30-meter diameter telescope, which they named the 30-meter telescope because astronomers are so imaginative,
So creative.
we spent a lot. They spent a long time on that. We should just call it a telescopic telescope face. And Native Hawaiians said no. They protested because the mountain is sacred. It is Hawaiian and is violation of Indigenous rights. And so there's been a lot of discussion in the field about that, because whether it's about the idea of science, the rights of science and needs of science versus Indigenous rights, we have to learn to be better partners with peoples on whose lands we work. And so it's been a big change in the field in the last decade.
Yeah. Well, that's an interesting point. I hadn't thought of that, but yeah, certainly a lot of telescopes on mountains, and Hawaii is a good place for that. So
yeah, one of the best places in the world.
Yes. Yeah, there's shipping, there's transportation, and it's still remote. So yeah, that makes a lot of sense. So, okay, well, you have a certain expertise in knowledge in measuring the distance to Polaris, among other things. At least in a couple things that I read from you. But maybe it'd be good how to cover how are the distances to stars measured in general? Different methods, yeah.
For most stars in our galaxy, we try to use a technique called parallax. This idea has been known for millennia, but it was only in the last couple of centuries we've been able to actually detect this for stars. And what parallax is if you observe a star some distance away, and there's a whole bunch of stars behind it, as the Earth goes around the sun, that star is going to move a little bit around. And you can measure that as an angle. And that angle tells you how much that movement is, tells you how far away the star is. If it's really close to us, that movement would be a lot. If it's really far away, it goes to zero. And so we try to use that. But it's hard. I mean, the amount is fractions of a degree, fractions. If you take a degree, chop it into 60 parts, chop that into 60 parts, and divide that by 1,000. That's the kind of numbers we're looking at.
So 1,000th of an arc second?
Milliarc. Yeah, we use the idea of a milliarc second. Yeah.
Okay.
Measure, and then we convert that to a distance. But basically, just 1 over that is the distance in parsecs.
Okay.
Which you may remember from Star Wars. But parsecs is a unit of distance. And so we use that, and we can measure distance to a lot of stars. Today, there's a space mission called Gaia, which isn't an acronym. It's actually called Gaia. That's ran primarily by the European Space Agency, and it is a satellite that's sitting out in the Lagrange point, orbiting the sun along with us, and it is measuring parallaxes of billions of stars all at the same time, almost our entire galaxy and a little bit of the Magellanic Clouds that you can see from the southern hemisphere.
Wow.
But the problem with that, to bring back to good old Polaris is a bright star, and Gaia can't observe it.
It's too bright.
It's too bright. This is the problem when you build big telescopes. You can't do any work with the bright stuff.
Wow. Okay.
And so there have been ways of doing this. What they did instead is instead of looking at Polaris, well, Polaris is also weird in other ways, in that it has a companion star. So really, when we talk about Polaris, there's Polaris capital A, which is the North Star that we talk about. Then there's Polaris capital B, which is its companion. Then there's also, orbiting closer to Polaris A, is another little star called Polaris capital A little a, because again, astronomers are creative. I'm sure there's an astronomer whose children are named A, B, C, D. And the other star, Polaris B, has its own little companion. What Gaia has done is we've been able to measure the parallax to Polaris B.
So Polaris B is
its binary companion.
It's far enough away from the others that the field of view doesn't get spillover from the too bright Polaris.
It's a really cool system because it's what we call a visual binary. Like you can watch Polaris B go around Polaris A.
Okay.
And it takes about 27 years. So you need to spend some time watching it. And like I said, it's far enough away that you can sort of separate the components in terms of the light, and you can actually measure the parallax that way.
Okay.
But it's hard because it's a binary system. There's not just the wobble that you see, there's also all the kind of binary movements. So you have to be very careful with the analysis.
Yes, you have to analyze and figure out the wobble, because they don't orbit the bigger star, they orbit the barycenter of the system.
Yeah. Yeah.
So then you want to know their mass.
Well, we can get the mass from that motion. You don't even know the mass to remove that wobble, but you can take that knowledge and the orbit and measure the mass. So this is a project a colleague of mine, Nancy Evans at Harvard, has spent decades working on, trying to measure the mass of Polaris. and she finds that it's about 3 to almost 4 times the mass of the sun.
Okay.
Which is another weird problem that we might get into later. But we have all these kinds of issues going on, and that's how we measure the distance today. But there's been measurements of distance to Polaris for 20 years, and they almost all disagree.
Now, how much do they disagree, though?
So on the low end, the lowest measurement was about 100 parsecs, or 330 light years. If I'm doing the conversion properly, I never think in light years. Sorry. And on the high end was about 160 parsecs. And so that times 3-ish, 3.25.
Okay.
And in light years. And with Gaia, it's just under 140 parsecs. So it almost splits the difference.
Okay.
But techniques have been basically between there. And it's very important because that distance tells us, helps us understand the mass of the system, because the mass and the distance from the binary of the orbit that you're mapping out, you need to know the distance to get the mass. It tells us about the state of evolution of the star, like where it is in its life cycle.
Mm-hmm.
And it's also very important because, as I'm sure we'll discuss, it is a Cepheid star. And Cepheids are a really cool class of supergiant stars that are really bright, and we use them to measure things like the expansion of the universe. And Polaris is the nearest one to us, so we kind of want to get that one right.
Yeah, okay. So, what is a Cepheid star?
So we like to think of stars as being pretty stable, round objects, but a Cepheid is a supergiant star, so it's really big. And over, say, a week or 2 weeks, you'll see its light get bigger, or its light increase. So it looks brighter, and then it dims and brighter and dims. And it just oscillates its light back and forth very periodically. And so the Cepheid is what we call a pulsating star. What's happening is its outer layers are expanding and contracting. And it is almost like a constant miniature explosion that's going on. And it just goes in and out.
Yeah, it pushes out, and then the gravity pulls it back in. Okay.
Yep.
And on the order of a few days.
On the low end, a few days. On the long end, 110 days.
For Polaris or for Cepheids in general?
For Cepheids in general. Polaris is on the low end at about 4 days.
Okay. So why is there an upper bound to that? Do we know that?
The upper bound has to do with how this explosion happens. So, as you said, when gravity pulls the material in, the star should be heating up. But what happens is there's a layer near the surface of helium, where the helium is just at the right temperature that it can basically give up its electrons or take back its electrons. So when you heat it up, all the energy can go into the ionization or the helium ionization, and you keep compressing without heating the star. Eventually, you can't ionize any more helium. So then the star heats up, and the photons below are trapped, and eventually the pressure grows so that it bursts out, and you get that flash of light where the star brightness increases really quickly.
Oh, so the photons escape. Mm-hmm. Sort of, okay.
Yeah, the photons push out, and then they escape. The materials, then the layer of the star is moving outwards, and then gravity kicks back in, and the cycle begins again.
Okay.
So the upper limit is sort of that layer of helium is getting to the point where the star is so cool that the layer of helium is too deep for this mechanism to work.
Oh, okay. So now when the photons are trapped, that's because the material is so dense that they hit things on the way out and get reabsorbed and re-emissioned, right?
Yeah. So we use the term opacity. So you can think of opacity is basically like a fog. And so when the photons are being blocked, is basically the point where the opacity is at highest, or the most foggy. And then but you build up enough pressure, the material pushes out and the opacity drops, so the photons just stream away.
All right, that makes sense. The fog. That's a great way to describe it. What are you drinking there? I've got my Toonshine.
Oh, I'm just having a coffee, a decaf coffee.
Okay. Um, I, people called it Toonshine. It's not. It's zero proof. Don't worry.
No worries, it's all good.
Uh, all right. So that's a Cepheid, and I had been mispronouncing it incorrectly in my head.
It's a Cepheid.
Cepheid. Okay.
It's from the constellation Cepheus.
All right.
The prototype, or the first star known of its type, was discovered in that constellation. Again,
Okay.
astronomers and their imagination.
They can't think of anything new. I suppose some astronomer might name their child 7 of 9.
Probably. If they had 9 children, they might.
If they knew that they were going to have 9 children. I don't know. I hope the Trekkies are appreciating that. So let's see. So what is, you said a 30-meter telescope. You talked about that. So what's the state of the art in telescopes and their ability to measure the parallax? What's the smallest amount of parallax that they can measure?
I can't think of it as an angle, but the Gaia satellite, which is doing the work, the 30-meter telescope won't really do this, but because you need really good stability.
Okay.
And I think the distance for Gaia that's measuring out to is, well, it's out to the distance of the Magellanic Clouds, which is 50,000 parsecs. So,
okay.
But 150,000-ish light years.
Okay. So is that outside the galaxy?
Yep.
Okay.
That's it. The Magellanic Clouds are our nearest large galaxy friends.
Okay. Okay. That's cool. And that's on the Earth. What about
that? Gaia's in space.
Gaia's in space. Yeah, sorry. Gaia's in space. And you said that's at Lagrange. Is that at Lagrange 2 on the outside?
Yeah, it's on Lagrange 2. We tend to put a lot of telescopes at Lagrange 2. The James Webb Space Telescope just arrived there recently. We've had cosmological telescopes go there. We're kind of piling up a lot of telescopes out there.
Yeah. Hopefully it's not getting too crowded. There's plenty of space.
I believe I have it right that Gaia is at Lagrange 2. I could be wrong.
It would make sense. You wouldn't want it closer to the sun, would you?
No, you wouldn't want it closer. You'd want it in following the Earth's orbit primarily, and that way you could sort of go. You also get away from a lot of the reflected light and stuff in the Earth and the sun and the moon.
I suppose we should mention Lagrange. The Lagrange points are points of gravity, neutral gravity in a orbiting system. So you can put something in these different Lagrange points, and there's 5, right?
Yes.
That don't need a lot of guidance, to stay in kind of generally in the area. So Lagrange 2 is, you got the sun, you got Earth, and then you got Lagrange 2 on the other side. So it just kind of goes there, and it sort of just orbits nothingness, just because of the way that the gravity potential.
Well, it goes around the sun still, but
yeah, but don't they? There's a small orbit around the Lagrange point that they do, right?
It depends on how stable it is. I'm not a huge expert on this part of the
okay
of the telescope placement.
All right.
I like the pretty pictures more than I like actually having to put the telescope in place.
Exactly. Okay. So so the distance to Polaris that Gaia measured was, you said 140 parsecs?
Yeah, about that, yeah.
Okay. And that's somewhere in the middle. And so as technology advances and our ability to measure things advances, we get better and we improve our measurements. So would the older measurements, do they have error bars? How much do they do on their analysis to include error bars? And are they all overlapping, or are we looking at it saying, oh, they're not even overlapping? We're a little sad about that.
Yeah. So depending on the technique, you get different errors. So with parallax, you'd have a statistical error from sampling, and as well as a systematic error, which for Gaia, I think is of would be about plus or minus 1 parsec or so. For Hipparchus, which was an earlier space mission that was doing parallax, it was plus or minus 4, I think, parsecs. On the low end, now some of my colleagues was based on the idea that Polaris was part of a cluster, and there are methods to measure the distance to a cluster based on how the stars appear to move. And so his error bars, I think, were plus or minus 5 parsecs. Okay. So the errors actually never agreed.
Yeah. Okay. So that is interesting. Yeah.
It has been a very long-going debate. Well, I wouldn't say it was a very popular debate. It's a debate between a few people and their preferred methodology.
Yeah.
I use methods where I was doing modeling of the star to say something about the distance, and you get limits with that. You could do it there was parallax with the Hubble Space Telescope that was done. That's where the 150 came from. And so we all had these different methods and perspectives, and parallax is a kind of an interesting kind of field, because there's not that many people who are qualified to do that analysis, and they tend to argue a lot.
Is this like argued out in papers back and forth, or is it done at conventions, or do they just they meet somewhere in a back alley and
I would sell tickets to the back alley event.
Yeah,
I think it would be funny. But yeah, usually a lot of the discussions are like conventions and meetings, not so much in the journal articles.
Okay.
You got to be somewhat polite, because they're also the people who are probably refereeing or reviewing your paper.
Very true. Yeah.
So it's a dance between criticism and politeness, I guess.
Yeah. The topic of peer review is something that the science deniers tend to just hand wave. They think it's paying your friends to tell you that you're right. I've heard people say that. And what I do know about peer review is that it's pretty much the opposite. That you're paying people to shoot you down.
Usually that's how it goes. I think peer review as a whole system has a number of problems, in my opinion. I think there are people who can, there's sometimes papers skate by based on name recognition or stuff like that, but as well as the fact that nobody gets paid in peer review. So this is sort of, it's this weird phenomenon where journals make money, but the people doing the work don't.
Yeah. So you send to a journal and you pay.
Depending on most journals,
depending on the journal. And then they find the peers to review it, and they don't get paid. And do you know who they are ever? Do you find out? Is that published? How does that happen?
Depending on the journal. Some journals are always anonymous. Some journals allow you to self-identify. Some journals, I'm not aware of any journal in astronomy, at least, that clearly says who the referee is.
Okay. And you've got a number of you say refereed papers yourself. So are there any, like, I don't know, how interesting are the stories to tell about that? Like, what kinds of things do you get back in your reviews? Have you had things kicked out and never published in the end because you had some big error in it, or?
I don't think I have anything that was never published. I've been rejected by some journals, so you can go from one journal to the next, and because sometimes depending on the referee, sometimes that's the problem. Usually, I think most of my referee reports are fair. Sometimes a little bit harsh. Usually, the silliness is you can identify a referee based on what they ask you to cite.
Oh.
So you'll sometimes get asked for references. Only once had I ever had a bad experience, and that was a paper that was rejected. And then a couple months later, I was asked to referee a paper, by them because I recognized who the referee was, and it was almost the exact same work.
Oh no.
They were using their own methods, but it was the exact same kind of idea.
Okay. Do you think that your idea sparked them then?
So I had back and forth with the journal, that particular editor and the journal. They said no, that it wasn't sparked by this. It was just people working at the same time.
Okay. Yeah,
But
certainly that happens. The discovery of Neptune.
it happens.
Right, yeah.
But the fact that, he threw my paper out and wanted his to go into the journal was a little creepy and cringy. So
I suppose we do have a guest flat earther in the live chat right now, who a good guy, lives near me actually. He goes by Effed Up World, and somebody said in the chat, no peer-reviewed scientific paper supports a stationary Earth. Because of course flat earthers generally don't just say that the Earth is flat; they also say that it's stationary. So.
well, we had journal articles pre-Galileo. There would have been.
Yeah. Makes sense.
And in fact, this is actually one of the arguments that kept the idea of a stationary Earth going for so long was the problem of parallax. Because people thought the stars were so much closer that if we were going around the sun, we would see parallax all the time.
Oh, yeah, their estimates were too close.
The belief was that the stars were closer than they really were.
Yeah. Huh? I suppose that makes sense. So what other than parallax, what are the different ways that distances are determined?
So we can use the fact that stars pulsate, like Polaris, offers a number of ways to measure its distance. As I mentioned, the period of that variability is like a few days to 100 days, but that period is correlated with how much light the star emits, and so that's called the Hubble law. So we can apply the Hubble law to measure distances to a lot of stars, and we do this to measure distances to galaxies out to almost 1 million parsecs away.
Okay. So that's if I can understand this, the amount of light that it emits is known within a certain range based on its behavior. And then we can measure the amount of the light that we get, do the math with the inverse square law, and then we know approximately how far away. Okay.
Because of the period, like if the star were a light bulb, based on its period, we could tell whether it's a 40 watt or a 100 watt light bulb.
Yeah, okay.
And by how much light we see, you just trace back the distance. But for stars like Cepheid, we also have geometric methods. This is a methodology called the Bada-Vesselink method.
Okay.
And what it does, it uses this pulsation to help measure the distance. And so we have the pulsation in the light, but as I mentioned, the star is expanding and contracting. And you can measure that expansion and contraction by measuring a spectrum. So you break the light into its constituent parts, and you see all these absorption lines of hydrogen and helium and iron and whatever. And those lines are going to shift back and forth. They're going to be Doppler shifted, because when the star is expanding, there's velocity going towards us, and when the star is contracting, there's a velocity going away from us.
Oh, it'll shift the
lines, yeah.
Oh, very nice.
And so if you can measure that radial velocity properly, you can convert that into a size of the star, radius of the star. Then if you have a way to measure how big the star appears to be, you can measure the distance. And so there are a couple of ways of doing that. One is we can use the spectrum again and try to measure how hot the star is, and that gives us a measure. That and the amount of light tells us the size of the star appears to be as an angle. Or we can use a group of telescopes called an interferometer. So you've seen this in radio telescopes, like you've seen the VLA in the movie Contact. You have all these radio dishes. They all work together as one telescope as an interferometer. We can do that with optical telescopes too. And so if you have a few telescopes pointed at the star, what you'll measure is a fringe, or if you remember, like Young's double slit experiment, where you get the light going through two slits and then it splits in the fringes. Same idea. So you get the fringes from these telescopes, and that tells you how big the star appears to be on the sky, how the angle as an angle.
Okay. Because
And so if you
in
have
general,
angle,
the angle is too small to just say, well, this star is this certain angular size. They're just
you wouldn't, yeah, with a regular telescope, they're all point sources, but with
Yeah.
an interferometer, you can measure it, at least for the brightest stars like Polaris.
Okay.
And with that angular diameter and then the radius from mapping the velocity movements, the ratio of those two things gives you the distance. And so we call that the Baudot length method, named after a couple of scientists from beginning of the 20th century. Sorry.
Okay.
And so we can use that to measure distances. One technique I've worked on is to measure distances using stellar evolution. So because Polaris is a Cepheid, it is at a special state of its evolution. It's gone through this. It's much more massive than some, so it's gone through its sunlight phase. Now it's a supergiant, and it's probably burning helium in its core and hanging out doing stuff. And we can compute models of stellar evolution and find out how much light should be emitted by the star by fitting other things like the temperature, its radius, and so on, and it's also its period, the period of variability. And doing it that way, you can sort of constrain the distance. We've taken a step,
an upper and lower bound on it, then.
At some level.
Yeah.
And I've worked with groups to take this a step further, because not only do Cepheids vary periodically, that period changes with time.
Yeah.
So, as the star evolves over centuries, that period might get longer or shorter. And that period, we call that period change, because again, imagination. And that is a measure of that's real-time stellar evolution. So if we can actually compute models to test that, we're doing real-time stellar evolution. And we were able to put constraints on the evolutionary state of Polaris, which told us that the distance had to be at least greater than 120 parsecs. So we were in the right ballpark. And these things are coming together in that respect. This was also a problem with the Polaris being 150 parsecs, because its evolution almost didn't make sense. It would have to be way more massive and almost a different star.
Okay.
So we have a multitude of methods.
Yeah, and that gives us a range then. Okay, so Polaris is a bit of a problem child, it sounds like, for measurement of distance measurements. But are there stars that are like the really well-behaved one where like we know this one within a really close range?
It's not so much any particular star that I can think of where we know is parallax to a really precise number. Largely because if we do it and it's so well behaved, I probably, most of us wouldn't bother studying it.
It's less interesting,
Yeah. But as the statistics is having groups of stars, and there's a lot, a lot of stars we have that kind of information. I think Sirius would be one. There's a star called Procyon. A lot of these sun-like stars, we have very good nearby sun-like stars. We have very good handle on.
And they're bright.
Yeah.
Right. Okay. Awesome. Are there things then, specifically for Polaris, where there's projects that are to do something new about Polaris that maybe aren't quite there yet, but are in planning, or maybe people are hoping for?
Polaris is a hard star to do an observing project because it's almost all professional telescopes. Polaris is too bright. But a couple of things have been tried is to look for X-rays from Cepheids.
Okay.
Which has been successful for a couple of cases. And the X-rays are important because it tells us about that when the stars are pulsating like this. If there's X-rays, that's evidence of a shock wave propagating in the atmosphere.
Okay, so you get the pulses of X-rays.
Pulses of X-rays.
Yeah. Okay.
I have colleagues at Queen's University in Kingston, Ontario, who have been measuring magnetic fields in Cepheids, and I think, well, I shouldn't say anything because it's not my paper to talk about and it's not published yet. But I think the results for Polaris are quite interesting.
Okay.
So magnetic fields are kind of one of the hard things to do to measure in stars, because for stars like the sun, the magnetic field's all kind of tangly and you can't really measure it or resolve it. But for massive stars, magnetic fields can be very well structured, but they shouldn't really exist.
Oh.
Because the magnetic field in the sun comes from this in the outer layers where everything's kind of bubbling and convecting, but massive stars don't really have those layers. So if you have a massive star's magnetic field, it should be from when it was born, and it should decay and fade away. Yet it persists in a lot of cases. And so there's some interesting evidence in that realm. And I think for me, one of the things I find very interesting, and this is something that I think is being taken on by a lot of astronomy enthusiasts, amateur astronomers and so on, is to keep mapping that pulsation period. Because as the pulsation period is changing, we're learning about the star. But we're also seeing things like the amplitude of that pulsation is changing with time as well.
Okay.
And so, it's been suggested a couple times in the past, maybe Polaris is not going to be a Cepheid much longer, or maybe it's doing something different. And trying to understand that kind of shift in stellar evolution is very important and interesting. And it also helps that Polaris is like 4 stars, which is just weird on its own. And constructing a system like that is stable over the evolution is really interesting and something worth trying.
And how far are the different stars in Polaris from each other?
This depends on the distance you measure, but Polaris, the main 2 components have a orbital period of about 25 to 30 years. So they're well separated.
So how's that compared to our solar system then?
So in our solar system, 30 years is what? Neptune-ish? I never remember the orbital periods of the planets. I'm one of those bad scientists who can't point at anything in the sky. And so, 30 years it's a long time. And that's, so we're talking separations of like whole solar systems.
Yeah. So it would be on the order of the size of our solar system for just these stars to orbit each other.
Or probably greater, yeah. Because you also remember the mass of the system is about 5 to 7 times the mass of our sun.
Yeah.
The Polaris, 2 stars together.
So, are there exoplanets around Polaris that that people have discovered?
Nobody's discovered an exoplanet.
Okay.
That would be really hard to do. We've never discovered an exoplanet around a giant or supergiant star. It's just too hard to do.
Okay.
And if we find one around Polaris, I think minds will be blown, because it would be a place where we really shouldn't expect exoplanets to exist. The problem with having exoplanets is you have to be able to form them, and stars more massive than twice of our sun. Their evolutionary timescale is so short, planets wouldn't even necessarily have time to form or evolve anything much. And so it would be expected that if there were planets there, it would be a disk that planets could form in would be unstable and kind of break apart pretty early in its lifetime.
Okay.
But if we find a planet, that would change a lot of things.
So, and I think this is a good example. Like the comment the idea about how planets and stars work say that there should not be a planet. But if somebody were to come along and say, "Hey, I found a planet orbiting Polaris," everybody would be skeptical, but be super excited, and would love to hear that their ideas were wrong, and then be able to roll up their sleeves and dig in and find out what's the right answer.
Yeah, I mean, our whole field of exoplanets has almost been one surprise after another, whether it's the first exoplanets that were discovered, which predate like the Kepler Space Telescope and these things, because they were exoplanets found around neutron stars, which, so some of these would be like diamond planets, just completely wacky.
Yeah.
And then a lot of the planets we found, first exoplanets we found were planets that were like Jupiter, but they're closer to their host star than Mercury is to the sun.
Oh, wow.
Which doesn't make sense because we don't know how that would even form. Because you have to build, if when you're that closest to the star, things like hydrogen and helium are too light. There's too much heat, so that the hydrogen and helium should be blown away.
Yeah.
So you shouldn't be able to form a very dense atmosphere. And that made up a large fraction of some of the early exoplanet discoveries. Now we're really in this phase where we're trying to find things that look like Earth. And there's a system called TRAPPIST, which is a very cool star, very small star, and the system has a whole bunch of planets. Some of them might be like Earth, and trying to find that stuff out. And so it's a very exciting time because we have all these new missions coming up in space, Ariel and Plato, and things like that. These are satellites that are being built by the European Space Agency, NASA, the Canadian Space Agency, and we're going to be able to start characterizing their atmospheres of these exoplanets and figure out if there's things like oxygen, which would be a sign of life, or maybe methane, or who knows.
Methane may be a sign of life too.
Mm-hmm.
Sometimes. All right, let's see. What has Hubble done in regards to Polaris?
Yeah, so the Hubble Space Telescope was a very useful tool for mapping out the orbit. So my colleague Nancy Evans has spent years kind of mapping out, using Hubble to map out the orbit, as well as not Hubble itself was used for parallax, but on Hubble there's something called the fine guidance sensor. You can think of like a finder scope on a normal telescope, on a telescope you might have, and that was used to measure the parallax of Polaris not that long ago, only about 5 years ago. And they found this is where they found the very large distance to Polaris using parallax from Hubble.
Okay. What about the big news, the James Webb Space Telescope? Are there, I suppose Polaris is a little bright, huh?
A little bit too bright.
Yeah. Okay. So that's, I mean, that's, hope the size of the mirror on there is pretty big.
It's a 6 meter telescope.
Yeah.
So it's way bigger than Hubble, and Hubble barely can, if you point Hubble at Polaris, you can barely do it without burning out the telescope.
Yeah. Wow. All right. So probably not a lot for Polaris, unless maybe they can look at one of the smaller ones, huh?
Yeah, for things like Polaris, what you really want are micro satellites. So there's a constellation of a set of telescopes in space called BRIGHT, which are, for lack of a better phrase, are basically digital cameras thrown into space, and they point at stars for a very long time.
Okay.
If you have good stabilizers, you can stare and do things like study pulsation, which we call astroseismology, or look for exoplanets, things like that. And if we had a couple of those in space for Polaris, that would work well. But the ones that are there now are kind of doing their own thing. And I'm not sure if they can easily be pointed at Polaris, because Polaris is also at a kind of a weird point.
Yeah. The angle to it is different. So it's good for finding your latitude, but a little bit more of a challenge if you're trying to point a telescope at, especially on Earth. Like Hawaii probably would not do very good imaging Polaris.
You can. So my colleague who's studying magnetic fields is using the Canada, France, Hawaii telescope on Mauna Kea. Okay. It's possible at the right seasons to do it.
Okay.
It's a little low in the sky, but you can do it.
So you'd want to. Yeah. Okay, that makes sense. All right. So what? This is a good one here. I thought you do things with a little bit bigger telescopes than a lot of people have access to. But what can people do themselves to learn for themselves about stars? Maybe if they have a very small budget.
Ooh. So I'm trying to remember the acronym's AVSO. The American Association of Variable Star Observers is an organization where it brings together enthusiasts who have telescopes and can map out things like, the time observations of things like Polaris or Mira or other really bright stars. And they have a lot of online resources to help people learn as well, and that are low budget, to start off and going from there. So that's aavso.org.
Right. People are asking, am I looking for questions? So I have a few more questions, but if you guys have questions in the audience, just tag me in the tag Toon Show in the live chat, and I'll get them down. I've got a couple coming up from the audience already. So
Good.
All right. So yeah, would you say AVSO? That if they have a telescope, maybe.
Well, if you have a telescope start, but they have resources to start you off
Okay.
learning. Because
Okay.
their job, they focus on variable stars like Polaris. So that, they'll give you a lot of the background science, the physics, things like that if you want to learn. And they're trying to think of other resources, but that's kind of the best one that comes to mind right off the top of my head.
Okay. Now, what if somebody wanted to see, look through a telescope themselves, or be involved in kind of a just an exploratory way through a university or some sort of a group of people that own a telescope? I don't know. There's clubs and things, right?
Mm-hmm.
How might somebody do that if they're interested in getting involved, at least just maybe in a entry level?
Yeah, I'm not an expert on the U.S. Availability. In Canada, we have a national organization for this. I think in the U.S. there's a lot of regional organizations. Like there's the Astronomy Society of the Pacific that does some of this, and almost many universities will have a planetarium or an observatory if they have at least one astronomer or so, and many universities will have open houses where you can come in and do viewings in the telescope and learn about some interesting thing in astronomy for the day and have a tour. And that's fairly common. And I know across the United States, there are a whole bunch of great clubs and for astronomy, for dark sky protection, for all these kinds of things.
Dark sky protection. Like, what's your opinion on Elon Musk's satellites there?
I'm sorry, I'm trying to think of a polite way to say this. I have a very low opinion. It's a vanity. It's going to do some good. I know of people in Canada and around the world who are using the internet through Starlink, but this is a beginning of a worrying trend. If right now there are about 5,000 satellites in space, another 10 to 30,000 pieces of debris that people are tracking, and in the next decade, there are plans to put up tens of thousands of more satellites.
Yeah.
And that's going to damage astronomy for one thing, but I think it's also when the satellites are in low orbit and they reflect a lot of light or are bright themselves, they're changing how we view the sky. And I think that's kind of wrong and disappointing. I mean, light pollution is already disconnecting us from the sky in many places. And and I think my own personal opinion, I hear all the time that being in nature is good for your health, but being in nature is also having a dark sky and being able to see the night sky.
Certainly. I my parents used to have a cabin in northern Minnesota, and I loved going there because even if the shade was open, I'd wake up in the middle of the night and open my eyes, and it didn't change how black it was. I just love sleeping like that and just having darkness like that. So, yeah. And I live in a city, and it's always bright. So, Hmm.
Yeah, I joke, and I live in Toronto. I have a fairly good view of the sky here, but I can only ever see a few stars. If I
Yeah.
walk downtown, I'm more likely to see more Canadian TV stars, if such thing exists.
Yeah. You mean Bubbles? It's the only one I know of.
But I don't think Bubbles lives in Toronto, unfortunately.
He, last I checked, Bubbles lived in a shack with his cats.
I went to school in Halifax, Nova Scotia, where that's filmed, and they were well known in that area.
I have a friend, John Snow, who lives in Halifax, and he's a very strange guy, and we all love him. Um, he comes on here every once in a while, and he's great entertainment. But yeah, he would get along with them, I think, pretty well. For people that are wondering, this is the Trailer Park Boys, a TV show that I'm talking about. Uh, can't let an inside joke go for too long. I don't know if everybody's gonna recognize that. Check it out if you dare. It's a bit of a crazy show. All right. What would you? You're a professor, and so you have students in astronomy. So what would you say to somebody that was thinking about pursuing a career in astronomy?
I think I would say astronomy is great in that it's all a whole bunch of questions. There's always going to be questions. I think astronomy is a difficult field to break into. It's not a lot of jobs at the top end, and there's not a lot of professors relative to the number of students.
Hmm.
So you have to be, if something you want to do, you really have to want to do it, and you have to do a lot of work.
Yeah.
And I think for students who want to study astronomy, they should read and learn about how we view the universe and cosmology and astronomy, as well as learn things like programming, because everything we do is on computers now. You have to have some math skills and physics skills. And as we are having missions to Mars and other planets coming up again, maybe learn a little biology and chemistry, and because astronomy isn't its own science. It's a bit of every science. So
Yeah.
that's really, I think, where we have a lot of fun. We get to do a bit of everything.
You use the word science, and yes, astronomy is a science, but flat earthers tend to deny science, and one of the ways they do that is by redefining science. To be super narrow, such that they even redefined what an experiment is, and so much that it says that only and the only valid experiment is one where you specifically modify the independent variable. So you can see how super narrow that is, and in astronomy you can't personally modify the location of a star. And so then these people who are not scientists and have basically almost never any STEM education at all proudly declare in their echo chambers that astronomy isn't a science because of their super narrow definition. So what do you, as an astronomer and as a professor at a university that calls what you do science, what do you have to say about that?
I sort of get that definition. It's very much taking a very strict view of the scientific method. The scientific method is you observe a phenomenon, you propose an experiment, you do an experiment, you see if it agrees with the predictions or not, and then rinse and repeat, or move on to do something else. And in some respects, I get that as a very strict definition. But I think science is far more general than that. Science is the attempt to understand the observations of nature and the things we see. And we can come up with lots of models or lots of ideas, but it doesn't have to be tuning a dial and only one dial and that's it. We can come up with, there are many ways of doing science. You know, one of the things I like talking about is how Indigenous people have their own methodologies. And so, for instance, one of the things that's very interesting is to try to trace things like the movements of caribou herds. So we have caribou herds all over northern Canada, and they migrate seas every year, and the migration paths change almost every year. And there's no good scientific model or computer model that actually can predict it. But many Indigenous elders, knowledge keepers, they understand it. They've seen it for so much that they intuitively know how the herds will migrate and how to manipulate it. And so part of that is not just proposing an experiment, it's observing and over a long period of time to understand and learn. And I think I would have a very expansive view of science, probably more than some of my colleagues. And in some respects, I would invite people who are flat earthers to say, okay, you believe in a flat earth, tell me your model. Here's where your model fails. Now fix it. And if you can if you could debug everything, you're still doing science. The science might be wrong, but you're still doing science. And so I think I'm actually very much on the other side where I want to bring in more of the people like this into science and to have a discussion that's supportive of the models and what they're saying and how to build it. So if you want to tell me there's a flat earth, you tell me your model and I will help you say, well, here's a problem with it. Whether it's in the southern hemisphere, the phases of the moons are flipped. How are you going to deal with that? And having that conversation, I think it's very reasonable. And, when you invited me onto your show, I was reminded of a book I read by Lee McIntyre, How to Talk to a Science Denier.
I got it on my right behind me here.
Very good book.
Yeah.
And I think a lot of it, one of the things he talks about is how for many people who are in the more extreme science denial, is that it's not just about the science, it's other issues in the world or in their lives. And so I think we should be more supportive and open to not necessarily giving them a platform on the stage next to a Nobel Prize winner, but give them a chance to work on their models and see and talk through it.
Yeah. I like that. That's a good approach. What do you say if they don't have a model? There are many of them that have discovered that every model that they put forward gets tested and falsified. So they generally, a lot of them say, well, we don't have a model. We don't need one.
Yeah. My opinion of that is, okay, if you don't need a model, as long as you're not hurting anyone, go nuts. And I'm, there are people who will believe what they want to believe in the end, and there are people who will never want to have a honest conversation where their mind might be changed. So if they want to believe the Earth is flat, that's fine. I mean, it doesn't change the reality.
Yeah. All right. So I got some audience questions here. We've got Effed Up World, who is our token flat earther. None others have shown up here that I've seen. He says, now he asked a question. I asked him to rephrase, so I'll ask both versions of it. He says, ask the good doctor what he thinks about inferences opposing observations. And then stationary Earth is his observation. And then I asked to clarify. He said, we observe still ground everywhere where people have ever been on Earth. Any kind of rotation or motion is an inference, but it opposes the observation.
I think that's an interesting point. And so I always have trouble with this because I kind of agree. Things do look like they're kind of not moving or pretty still and everything's moving around us. But, that's a relative issue. Einstein kind of noted this very much too. Like if he's in an elevator falling at the acceleration of gravity, he's not going to be able to tell the difference between that and being on a planet.
Yeah.
I think what it's not an inference, it's that we're talking about here. It's a relative issue. Relative to us, everything appears stationary, but that doesn't mean everything is stationary. It just means we're moving with it.
Yeah. Yeah. In a car, your hands, the seat, the cup and the cup holder appear stationary. But you look outside and we figure it out.
I drive with a cup of coffee. It's not going to spill until I hit a pothole, which is, depending on where you are.
I've heard Canada has them.
More potholes than roads in some places. Yeah.
All right. Tiny Captain, who is an actual ship's captain, who is certified in celestial navigation. So he has pointed a sextant at stars and gotten his position successfully. Flat Earthers actually claim that sextants only work on flat Earth. I've challenged them with $10,000 of my own money to do it, to show how to do it. And for more than 40 days, none of them have been able to do it. I don't know. Anyway, Tiny Captain says, can you ask Dr. Hilding Neilson, what is the biggest angle when the Earth is on the opposite side of the sun? So maybe the biggest angle to a nearby star? Sirius, right?
Yeah. It's a good question. I don't know off the top of my head. Probably you're still in the
milliarc seconds.
Yeah, maybe centiarc seconds, or tens of milliarc seconds. But I don't, off the top of my head, I don't know.
Okay. And did I get it right? Is Sirius the closest?
No, Alpha Centauri.
Alpha Centauri. Oh yes.
Is the closest main big star or solar-like star.
Wait,
there are some really cool stars that are closer.
Oh really?
Yeah, we call it M-dwarf stars.
Oh.
Like they're very hard to see. So that's why we tend to say Alpha Centauri is closest, because we can see it.
Oh, okay. And all right, is my confusion that Sirius is the brightest? I hope I'm right.
Sirius is the brightest. Yeah.
There we go. I got something. I'll take that as a win. All right. So, all right. Well, Tiny Captain, there we go. We don't quite have a necessary answer. We got Waikikamu Cow says, can Dr. Neilson please show us the ruler he used to make all these measurements? That's flat Earth science.
Who measures? What ruler did you use to measure the ruler?
I've asked them that, and they get mad at me. Yeah, they've when in the 60s, people bounced radar off the sun.
Mm-hmm.
So it's a pretty basic and easy to understand way to measure the distance. We know the speed of light, and you do a little bit of math, and you find out how far it is away. And they are one of them. Their answer to that is, how did you measure the distance without going there? They really do think you have to have a ruler to measure the distance to something. But it's a good point. How was the ruler made?
I mean, and we've been speaking of parallax, we've been doing parallax of planets for centuries. We measure the size. So, Johannes Kepler and Isaac Newton, because of them, we were able to sort of say, how far away and our planets from the sun, but only relative to the Earth. So the Earth would be one distance, Mars 2.2, and so on. And it was only when we observe Venus passing in front of the sun from two different parts of the Earth were we able to sort of actually say how far away Venus is.
Yeah.
In miles.
You mean simultaneously?
Yeah. Well, yeah. It doesn't have to be simultaneously, but it's easier if you're doing it on the same transit.
Yeah.
You just have to know where in the two parts of the Earth you're at and how far away they are.
So you need to know the size of the Earth to do that, right?
In principle, yeah.
Yeah. Okay. Yeah, an interesting solution to that problem. I had another one that came through, but I lost it. You've got Mercury, right? Mm-hmm. which is what kind of god is that?
My Greek and Roman gods are not well known.
It's a Roman god, right? And you got Venus, which is a Roman god, and Earth or Gaia, which is a Roman god. And you got Mars, which is a Roman god, and Jupiter, which is a Roman god, and Saturn, which is a Roman god, and what's next?
Uranus.
Which is a Greek god.
Yeah, that's a little more has to do with the politics.
Just so that 13-year-old children like me can have a little chuckle at the name.
Well, the problem was when it was discovered almost simultaneously by astronomers in England and France. And this is in the 1800s, 1800s. So everybody's a little, patriotic and all this stuff. And so when it was discovered by the English, it was called St. George's Star.
St. George's. Okay.
Yeah.
And a star. They thought it was a star.
No.
Oh.
He didn't think it was a star. He just called it that.
Oh, okay.
And so it took some negotiation to get the name to be something else that wasn't so overtly Anglo-Saxon.
Okay. So, all right. So that's why the
chuckle about it now.
Interesting, because it's is it Cephas? I think would be the Greek name. I think I got that a little wrong. Anyway, then Neptune and Pluto, which are also Greek. So, yeah, Apophis Rex says Pluto is actually named after the Disney pooch. No, it wasn't. Okay. Let's see. Martin H says, does Hilding manage to get his eyes next to an eyepiece every now and then, or is it all computer screens and work?
Well, the thing with doing professional astronomy is we don't use the telescopes ourselves anymore. It's more efficient to have people do the work on site, and they schedule a whole bunch of different observations from different people. So historically, what we would do is the astronomer wanted an observation thing. We get 2 nights, so we go to the telescope for those 2 nights and hope for the best. But now what we do is we put in our kind of proposals, they organize them, and they do it as the telescope does it as it can. So we don't even have to go anywhere near the telescope to do this anymore. So if I want to look through an eyepiece, I'm stuck with that one.
Turn it a little farther. There it is. People can see it now. And what is, well, while you're pointing at it, while we're talking about, what is that telescope there?
Oh, it's just a small celestron power telescope, just a basic setup.
All right, hold on. I'm gonna let people see it a little better. There it is, just on the edge. All right, I'll fix that. So all right, so you I suppose you schedule it, you have to find the budgeting for it because they don't do it just for free.
Well, depending on who operates the telescopes, it's paid for by some agency or somebody else. So like Canadian telescopes are paid for, their time is paid for by the government. A lot of the telescopes in the US are paid for through the National Science Foundation. Some are provided by the universities, some aren't. So normally you don't have to worry about the budget yourself.
Okay. I guess that's nice, right? But yeah, so you'll put together a presentation and a proposal. They'll say okay, and then some number of days later you'll get an email, you'll get computer file. I mean, how's it delivered to you?
Usually when usually the data is taken, they'll put it on their database. You'll get a note saying you can download it or do what you want with it, run it through their analysis software or run it through your own. And there you go. And depending on the telescope, that data can be available to everybody right away or sometime in the future, sometime afterwards.
Okay. Cool. All right. Let's see. Okay. Not really a question, but John Michelson says, and yet they, the flat earthers, still deny the results of geodetic surveys, even when they used actual rulers, rods and chains, to do the most accurate triangulations. They do. All right, let's see. This is a good one here, I think. You might like this one. It says, what can be done to empower Indigenous people to become part of the scientific community? And thank you for advocating on behalf of Indigenous people.
I think that's a very good question. And it's something I've thought about a lot, and it's not easy. I think we've seen historically particularly in North America, that many Indigenous peoples have a good reason not to trust various leaders or even scientists, things like that. In Canada, we had the residential school history, from which was a significant damage to many peoples and many cultures. And I think if we want to work with Indigenous peoples more and have Indigenous peoples coming in the STEM, I think we need to spend more time listening and learning from Indigenous knowledges. I think a huge part of bringing people into science is having the ability for people to see themselves in science. If you have 100 scientists and they all look like me, that's a lot of people who are probably not going to see themselves in science. I think for many Indigenous people to see ourselves in science, it's to see the knowledges, see the stories, see the respect, and see the place. And it's very important. We've been talking about how pulsating stars. The first pulsating star discovered by European was in the 1500s. But Indigenous peoples in both North America and in Australia have known about pulsating stars for millennia. It's in their oral traditions.
Oh.
And all these things have existed. And so just listening and learning and respecting, I think, would be a great step forward. In Canada, particularly, a lot of the discourse has been very dismissive of Indigenous peoples, and that we need to change that.
Well said. Thank you. And now to a different topic. A guy, It's Not Flat Dummy, says, ask him if he's seen the Batman.
Not yet. I'm looking forward to it. I'm a big fan of Batman. I'm hoping this is going to be a step up from more recent DC stuff.
Yeah, the actor who shall not be named. I didn't like. Nope. The one after the insurance company. Nope. We cannot say his name.
I kind of liked him as Batman. I think he kind of worked as an older Batman. It wasn't bad, but definitely wasn't the best. Nobody's ever going to be able to replace Michael Keaton.
Michael Keaton. There we go. All right. Oh, so much better. I have Batman cereal from 1989 up there. I've never had it on camera. I'll have to get it out sometime. Up on the shelf there. All right. Mute Donkey asks, what's your favorite type of space object?
Well, I tend to like stars because I think every star is a little bit different. They're very much like people. They have all kinds of weird little physical phenomenon, whether it's stars that pulse, stars that just blow off wind, stars that explode, stars that undergo astroseismology, which is space, starquakes basically. And there's all kinds of things going on in stars that's just really cool. And then you think about the fact that I have iron in my body, oxygen, I breathe oxygen, we're made of carbon, all these materials that basically everything but hydrogen, helium, and lithium were made in stars at one point or another.
Yeah.
So it may be a little bit glib, but in some respects, stars are our ancestors. And I think that's what makes them really cool. And we can relate to them. I'm also a big fan of exoplanets, just because it's a lot of fun trying to talk about whether planets are going to be made of water or planets that might have red grass or whatever. All these different things that are happening. If you have a star that's emitting mostly red light, photosynthetically speaking, it would be different.
That's true. Yeah. All right. Martin H says, What does Hilding see as being the main areas for breakthroughs in astronomy research in the next few years?
Oh wow. Well, the James Webb Space Telescope is going to be a breakthrough in the next few years, and it's going to do a few things that are really cool. One, I think it's going to find the first stars. And we have the universe. Astronomers, I would say that the universe was born in the Big Bang, and when the Big Bang happened, the universe was much hotter than it is today. And so when the universe cooled, we reached a point where there was no light, or the light was all streaming away because it was not interacting with anything. It was too cool. And eventually the dust could collapse into the first stars. And it's the first stars that reionized the universe, or created the photons that could ionize material and do things like that. And those first stars are going to tell us a lot about the universe and cosmology. I think James Webb is going to be the first telescope to do a lot of the exoplanet characterizations that are for things that are closely related to an Earth-sized planet. Like, we talk about things called super Earths or sub-Neptunes. Again, the imagination of astronomers is boundless. And, I think James Webb will go do a lot in characterizing these planets for the first time, and give great insights there too. So those are the two things I'm holding my breath for.
All right. Well, and that answers the question from Glober Mom, who asks what you think of the James Webb. So, so people have noticed on the shelf behind you some very cool, a Millennium Falcon there, and then what's over to the side there?
That's the was it the Razorback from The Mandalorian?
Okay.
Yeah. And of course, Baby Yoda.
Yes, everybody loves Baby Yoda. So, all right, that's cool. You can people have watched me put things together. The Lego globe here took 5 or 6 nights. I did that all during live streams. People sat there and watched me put it together. They're crazy.
I would probably need a explicit button if I were live streaming my Lego work. But
oh, yeah. I mean, you don't. It doesn't take much of a big project to have to redo stuff. you flip back. You're like, I'm missing a piece, or I have too many extra pieces. Like, I got to flip back. What did I miss? So.
Yeah, that's a few swear words right there.
Well, that's what I have for questions, and the audience gave a few. So, this has been cool. Very interesting. Anything that you'd like to add as we kind of start to wrap up here?
Yeah, I know we're in a very exciting time with the James Webb, but there is one thing we should be aware of with that telescope, and that's his name. It's named after a U.S. I can't remember if he was a congressman or a senator who was very influential in the space race.
I think he was at NASA.
He's a politician, but he was leading a lot of the funding.
Okay.
Or he was an administrator. But in this time, one of the things he has been found to be complicit in was the basically chasing off and removing a lot of people from NASA and politics for their sexual identity. And so this has been a discussion that many my colleagues in the U.S. have been putting forward, because it's not necessarily right to name a telescope or anything after a person who has done so much harm to a community of LGBTQ plus people.
Yeah.
And so, while I think the telescope is going to be great, I think it's also important to acknowledge, not everything is perfect.
Yeah. Yeah, it certainly is a conundrum of sorts, that he did good things and he did bad things. So all right. Well, thank you so much. It's been just a pleasure to be able to talk to you and to get some better understanding of Polaris in particular and stars in general. So I appreciate that very much. We'll wrap up. don't close the connection here right away. But everybody, thank you for coming. And I have just a little hint. I have a challenge. It's another celestial navigation challenge, and this one is to use actual globe math, and there's some funds involved. I think I'll be putting out a video tomorrow and then Wednesday, so be looking for those two because that'll be the important ones. All right, everybody, thanks, and we'll see you later.